All right, so here's what we didn't get time for today. Just how you kind of use this equation, right? So if you're looking at rotational, right, we have all of our things. We know everything up to here so far. Okay, so again, keeping kind of with that analogy, the work is going to be torque delta theta. Okay, and then the kinetic energy is going to be 1/2 I omega squared. Okay, and remember, when it's rolling without slipping, then you can use V equals R omega, okay, which is almost always. There's not usually rolling with slipping, okay? All right, so just a kind of problem how you'd be able to do a small rescue helicopter has 4 blades, okay? Each is 4 meters long, all right, and has a mass of 50 kilograms, okay? The blades can be approximated as thin rods that rotate about one end of an axis perpendicular to their length. Okay, so then if you go back to your little sheet, or you remember, I'm pretty sure this is the one that's 1/3 ml squared. Okay, 1/12, remember, was about the center. 1/3 is about the end. Okay, and the helicopter has a total mass of 1,000 kilograms. Okay, so the helicopter mass is 1,000 kilograms. Okay. All right, so first thing that we'll need to do is it says calculate the rotational energy of the blades when they rotate at 300 RPM, okay? So the K rotational is going to be 1/2 omega squared, I omega squared, okay? And I is going to be 4 times 1/3 ml squared, all right? Because there's 4 blades, okay? So 4 times 1/3, 50 kilograms, 4 meters squared. All right, and then of course I didn't bring the good calculator. That was dumb. So I have to use stupid iPhone calculator. Divided by 3 times 50 times 16. Okay, so the I is going to be 1067 kilogram meter squared. I'm just going to round it. Okay, all right, and then omega, right? We just know if it's 300 RPM, which is revolutions per minute, I have to get that into radians per second, okay? So hopefully you can convert stuff, your good old chemistry skills. 1 revolution is 2 pi radians, okay? So that means my omega is going to be 300 times 2 times pi divided by 60. 31.4 radians per second. Okay? All right. Let's see. All right. Okay, so then I'm just going to do K rotational, 1/2 I omega squared, so 1067, 31.4 squared. Okay, so then the rotational kinetic energy times 1067 divided by 2 is, whoa, is that right? That seems a little bit awfully, look. Seems awfully big, but maybe. 31.4 times 31.4 times 1067, yeah, that's kind of big. Divided by 2. Yep, I guess that is right. About 526,000 joules. I just rounded it, right? It's like 10 or something, but whatever. Okay, 526,000 joules is the rotational kinetic energy in the blades. Okay, all right. Then calculate the translational kinetic energy of the helicopter when it flies at 20 meters per second. Okay, so regular kinetic energy, translational, 1/2 mv squared. Okay, so the mass was 1,000 plus the blades, so 1,200, 4 blades at 50 each. So 1,200 kilograms times, I think it said 20 meters per second squared. Don't forget to square it. Yeah, okay, so then translationally, 0.5 times 1,200 times 20 times 20 is 240,000. Okay, so it actually has, in this case, about half-ish as much kinetic energy translationally as it does rotationally. Okay, all right, so that's kind of basically how you just solve a simple problem. You have to remember you're going to have to go back and do this which is the ml squared or mr squared in some form. Okay, and then they'll either give you this omega, okay, or if it's like a rolling without slipping thing, then you'll have to use that. Okay, but not for this problem. All right.